Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 6 exam for May-June 2022 variant 1. So let's get started. Question 1 says a student investigate the stretching of a spring. The apparatus is shown in figure 1.1. We have a spring on a clamp which is holding a meter rule. On figure 1.1, take two readings from the meter rule to determine the unstretched length L0 of the coiled part of the spring. So the uncoiled part of the spring starts at this part. So this part is at 21.3. So the first reading is 21.3 centimeters. And it ends at this point here, which is at 22.8. So we write down 22.8. And the distance between these two values, we can subtract 22.8 minus 21.3. That gives an answer of 1.5 centimeters. Part double I says draw a diagram to show clearly how you would use a set square to obtain an accurate reading from the meter rule. So using the set square to read the meter rule means that we are going to use a set square as a pointer. So we can draw the part of the clamp which carries the spring, and then we can draw the spring as a question mark, then a coiled part of a spring, and then an inverted question mark. Then we draw a rectangle for the ruler and a triangle for the set square, which is pointing towards the spring like this. And now we label the diagram. So here we have the spring, the set square, which is the triangle, and we have the rectangle is the rule or the meter rule. Part B says the student suspends a load of P equals 1.0 Newton from the spring. He records the new length L1 of the coiled part of the spring, and it's 2.2 centimeters. Calculate the extension E1 using the equation E1 is equal to L1, which is 2.2, minus L0, which we calculated in the previous page as 1.5. That gives an answer of 0.7 centimeters. Then we are required to calculate a value for the spring constant K of the spring using the equation K is equal to P over E1. So that's 1.0 divided by 0.7. That gives an answer of 1.4286. We can approximate that to two significant figures as the ones in the question. So 1.4. And we divided force Newton by distance in centimeters. So it's newtons per centimeter. Part C says the student suspends a load of P equal 5.0 newtons from the spring. He records the new length again, L5 for the coiled part of the spring. L5 is equal to 6.3. Calculate the new extension E5, L5, which is 6.3, minus L0 again, which was 1.5. That gives an answer of 4.8 centimeters. And we are again required to calculate K, but here we use the new load 5.0 divided by the new extension 4.8, and that gives a value of 1.0417, so approximately 1.0 newtons per centimeter. Part D says state whether your two values of the spring constant, which were 1.4 and 1.0, can be considered equal within the limits of experimental accuracy. Explain your answer by referring to your results. So if we calculate the percentage difference between them, 1.4 minus 1.0, and then we divide by the larger number, 1.4, and calculate a percentage times 100, that's actually greater than 28%, which is too large. So we say no, they are not equal because the difference is outside the range of experimental error, which should be between 10 and 20%. Part E says a student improves the experiment by taking additional sets of readings. Suggest the additional apparatus that the student uses. So we could use more loads or different values for the load. So we need additional loads to get different values for the extension. Double I says suggest how the student uses the additional results. So we can say to plot a graph of load against the extension of the spring. Question 2 says the student investigated the cooling of water. The apparatus is shown in figure 2.1. Part A says the thermometer in figure 2.2 shows the room temperature theta r at the beginning of the experiment. Record theta r, which is here 23, so 23 degrees Celsius. Part B says the student pours hot water into the metal can. She places the thermometer in the hot water. She records the temperature theta of the hot water at time t equals 0 and immediately starts a stop clock. She measures the water temperature every 30 seconds and the readings are shown in table 2.1. Complete the column headings. So for 30 seconds, the time is in seconds and the temperature is always in degrees Celsius in paper 6. And these are the values. Part C says the student pours the water from the can into a measuring cylinder and records the volume of the water, 196 centimeter cubed. State 2 precautions taken when reading the volume of water in a measuring cylinder in order to obtain an accurate result. So we say look perpendicular to the scale of the measuring cylinder and also look at the bottom of the meniscus of the liquid. Double I says the student records the volume V to the nearest 1 centimeter cubed. Suggest why this is appropriate. We can say that the measuring cylinder can be accurate to 1 centimeter cubed, which means the minimum division on a measuring cylinder can be 1 centimeter cubed. Question DI says calculate the decrease in temperature delta theta 1 of the hot water between time 0 and 60 seconds. So going back to the table, from 0 to 60 we have 84 and 75. So the change between 84 minus 75 gives 9 degrees Celsius. And then we are required to calculate the average rate of cooling R1 of the water using the equation delta theta 1, 9 divided by delta T, 60 seconds. So we divide 9 by 60. That gives an answer of 0.15, and the unit here is degrees Celsius for temperature per second for time. Double I says calculate the decrease in temperature delta theta 2 of the hot water from times 120 seconds to 180. Again, we go to the table. So from 120 to 180, we have 70 and 67. So we calculate the difference, 70 minus 67. That gives us 3 degrees Celsius. And we are required to calculate R2, which is delta theta 2, 3 divided by delta T, 60 seconds. So 3 divided by 60, that gives a value of 0.05 or 0.050. And the unit again here is degrees Celsius per second. Question E says a student suggests that the rate of cooling is lower when the temperature of the water is lower. State and explain whether the results support this suggestion. So the rate was actually lower at the second part of the experiment, and it did have a lower temperature. So we say yes, since R2 is less than R1, and for R2 the starting temperature was actually lower than for R1. Question F says the student states that most of the thermal energy lost by the water in the can is by evaporation from the water surface. Another student states that most of the thermal energy lost by the water in the can is by conduction through the sides of the can. The students repeat the experiment twice to investigate the two statements. Suggest one suitable addition to the apparatus for each additional experiment. So for the one with evaporation, we can add a lid or a cover. And for the one with the conduction from the sides, we can say that we are going to add insulation around the can to prevent heat going sideways. Question 3 says a student investigates the resistance of a wire. Figure 3.1 shows the circuit he uses. Part A says a student measures the current and decides that he wants to use a lower current. He adds a variable resistor to the circuit to reduce the current. On figure 3.1, mark with an X a suitable position in the circuit for the variable resistor. So it must be in series with the components connected. So we can, for example, point it here. It said label it with an X. We can place it anywhere on the wire already drawn. We do not form another branch or a parallel connection. Part B says the student measures the current I in the circuit. Record the current shown in figure 3.2 in this diagram. So this is 10 divisions from point 2 to point 4. So each division is actually 0.02. So the one right before 0.4 is actually 0.38. And the unit here is ampere. Part C says the student places the sliding contact at a distance L equals 85.0 centimeters from B. He measures and records in table 3.1 the potential difference V across the length L of the resistance wire BC. Record in table 3.1 the potential difference shown in figure 3.3. So this is 5 divisions between 2 and 3, so each division is 0.2. So 2.2, 2.4, 2.6. So we go to the table and we record 2.6 volts. Part D says the student repeats the procedure using L values of 65, 45, 25, and 5 centimeters. His readings are shown in table 3.1. Calculate and record in table 3.1 the resistance R of 85.0 centimeters of the resistance wire using the equation R is equal to V over I. So we divide 2.6 by 0.38 amperes, and that gives a value of 6.842105. So we approximate that to 2 decimal places as all the numbers on the table to 6.84. Then we are required to complete the column headings with the units. So the unit for voltage is volt and the unit for resistance is ohms. Question E says plot a graph of resistance R. Question E says plot a graph of resistance R on y-axis. So we label this R per ohm against the length on x-axis L, and the unit was centimeter, and start both axes with 0. So for the length we have the maximum number was 85 and the minimum number here on the graph is 0, and we divide by the number of divisions. We have 5 large divisions here. That gives an answer of 17. Choosing from 10 or 20 or 50. 10 is too small, so we choose 20. So we go 0, 20, 40, 60, 80, and then 90. As for the y-axis, the maximum number was 6.84 and the minimum number is 0, and then we divide by the number of divisions. On the y-axis, we have 4 large divisions. That gives an answer of 1.71. Comparing that to 1 or 2 or 5, 1 is too small, so we choose 2. So 0, 2, 4, 6, and 8. Now we plot the points. The first point was for the length of 5, so this is 10, 5 is at this point, against resistance of 0.53, so this is 1, this is 5, so 0.53 is approximately at this point. The next point is for 25 centimeters, this is 30, so this is 25 at this point, against 2.11, so 2.1 is here, 2.11 would be at this point approximately. We have to approximate almost all the points. The next one is for 45 and 3.68. So 45 is here and this is 3. So this is 3.6, this is 3.8, and 3.68 is approximately at this point. So this is the third point. The next one is for 65, which is here, against 5.26. So this is 5, this is 5.2, and 26 should be around this point, the fourth point. The last point is at 85, which is here, against 6.8. So 6.8 is here, 6.84 is about this position. So this is the last point. Now we draw a straight line. We try connecting the first and last points and see if it's a best fit. So it appears to be a best fit. So we leave it as it is. Now question F says use your graph to determine the resistance R50 of 50 centimeters of the resistance wire and show clearly on the graph how you obtain the necessary information. So we go from 50, which is midway between 40 and 60, and we go up there towards the graph. So this is almost at 4.1, so we write down 4.1 and the unit for resistance is ohms. Question 4 says a student investigates the force required to break different beams made from a mixture of sand and cement. All the beams have the same cross-section. Plan an experiment to investigate the force required to break the beams. Figure 4.1 shows the setup. We have a beam with a load on the beam at the center and 2 supports below the beam. The following apparatus is available: a selection of beams made from different ratios of sand and cement and of various length. So we can either choose the independent variable to be the length or the percentage ratio of sand to cement, and triangular blocks to support the beam, a meter rule, and a selection of loads. So we can use, for example, the meter rule at the base of the apparatus to measure the distance between the 2 supports here and make sure that this distance does not change. For example, we call it D and we say keep D the same. And we keep adding loads to the center of the beam and see which load breaks the beam from the middle. But we say that we are going to use beams with the same dimensions but different ratio of sand to cement. Or we can say we use same ratio of sand to cement but we change the distance D as an independent variable. So for example, I'm gonna use the ratio of sand to cement as the independent variable. It says you can also use other apparatus and materials that are usually available in a school laboratory. The student takes all the necessary safety precautions. You are not required to write about safety. In your plan, you should explain briefly how to carry out the investigation. You may add to the diagram if it helps your explanation. State the key variables to keep constant. Draw table or tables with column headings. Do not add any readings in the table. Explain how you would use the readings to reach a conclusion. So we can start by saying set up apparatus as shown in the diagram with the rule placed as close as possible to the supports and use the first beam. Now we measure the distance D between the supports and looking perpendicular to the rule scale to avoid parallax error. Then we start adding loads, so we add known loads on the center of the beam one by one until the beam breaks. Now we record the load and we give it a name L that breaks the beam. And now the experiment is done. We can now say repeat the above steps for an identical beam and record a new value for the load. For example, we can call this load 2 and the first one load 1 to calculate the average, and we give it a name, for example LAV for L average. And then we repeat all steps for beams with identical dimensions and same distance d, but the beams have different ratio R of sand to cement. So this is the independent variable here, and we kept the distance and the dimensions of the beam the same. Now we form a table here. The independent variable was R, which is the ratio and has no units. We measured the load 1 per Newton, load 2 per Newton, and we calculated the average load in newtons again. And these are the column headings. We do not enter any numbers in the table. We do not know what is the result of the experiment, so we keep it empty. And then we say plot a graph of the independent variable R on the x-axis against the dependent variable L average per Newton on the y-axis to compare the results. So this was the end of the exam. I hope you enjoyed this video and found it useful. Keep practicing, and I will see you in another video.